Hello everyone, I am Miss Hu, your physics teacher. In this video lesson, we will be learning about transformers in terms of what a transformer is and its function, the construction of a simple transformer, the operating principle of a transformer, the transformer equations, calculating the efficiency of a transformer, factors which affect the efficiency of a transformer and how to overcome them, the use of transformers in the transmission of electricity, and the power loss during transmission. That is quite a lot, isn't it? So the reason I put all of this in one video lesson is so that this video lesson is a complete lesson about transformers. So what you'll be learning in this video is all the theoretical content knowledge you need to know for your exams. And if you want to learn how to solve questions, those will be in a separate video. So let's get started with what a transformer is. Now the function of a transformer is quite simple. It's to change the voltage of alternating current circuits, which means that if you have an alternating current power supply, you may want to change the voltage, and the device to change that voltage is the transformer. So one thing you should be aware of about transformers is that they only work with alternating current. In your syllabus, you have to know that transformers do not work with direct current. So that's why in the function here, it's written that it's specifically to change the voltage of alternating current only. We'll go into more detail about how a transformer does this. That means how a transformer is able to change the voltage shortly. For now though, let's just go through the types of transformers. Now there are two types of transformers. There's the Autobots and Decepticons. Okay, no, that's from the cartoon and from the movies. Okay, the real thing here is this. The two types of transformers are step up and step down. A step-up transformer increases the voltage of the alternating current power supply, while the step-down transformer decreases the voltage of alternating current. So remember it this way, transformers are used to change the voltage. So step up means that the voltage goes up, increases the voltage, while step down goes down, decreases the voltage. It is important that you remember the transformer changes the voltage, not the current, because a common misconception that students have is that when the voltage increases, the current increases as well. That's not true. When the voltage increases, the current decreases. So why the current decreases? That will be addressed at the end of the video when we learn about the equations for a transformer. For now, let's just remember that transformer changes the voltage, step up, voltage goes up, step down, voltage goes down. This is the symbol of a transformer, and this symbol is actually based on the construction of the simple transformer. So let's go into the construction of a simple transformer. For now, we'll just learn about the basics of a transformer. Once we know how a transformer works, we can always modify it to make it more complex for different purposes. So that's why for our foundation, we just learn about the basic foundational simple transformer. A simple transformer is made up of three main parts. One of it is the soft iron core. So the soft iron core is basically a cuboid with a hole in the middle. So the reason why there's a hole is so that we can wrap two coils around either ends of the transformer. So the other two parts of the simple transformer are the coils. One is known as the primary coil, which is connected to the input circuit, while the other is the secondary coil, which is connected to the output circuit. Now, let's take a look at the operating principle of the simple transformer. How is a transformer that is constructed like this able to change the voltage, and why does it only work with alternating current? Well, first of all, we need to know where the circuits are. The primary coil is connected to the input circuit. The input circuit is where we will connect the alternating current power supply, which we want to change the voltage of. So I will draw in this diagram the alternating current power supply over here. So this is the AC power supply. Now for the secondary coil, it will be connected to an output circuit. The output circuit is where we would want to connect the device where we want to use the new value of the voltage. So in this case, just to represent that component, we'll put a light bulb. Now remember, the light bulb is merely a representation. You'd always place something else in place of the light bulb. Like you could put a motor, you could put your refrigerator, you could put your laptop charger. The lamp is just a representation of the load in the output circuit. So if you take a look at both circuits, you'll find that there's only a power supply provided at the input circuit. There's no power supply on the output circuit. And that's because the transformer is going to be inducing voltage on the output circuit. You must understand that the input circuit and the output circuit are two separate circuits. The current and voltage are respective in their own circuits. They are completely exclusive. The current that flows in the input circuit stays in the input circuit, and the current that flows in the output circuit stays in the output circuit. Some students think that the current would jump from one circuit to another. That's not what happens. The current does not jump from the input to the output. The current stays in its own input circuit. This current stays in its own output circuit. But what happens here is that the input circuit would cause a current to flow in the output circuit. Now, how does that happen? Let's look at what happens in the input circuit. So you must use alternating current for the input circuit. You can't use direct current, and this is why. Alternating current, as you should know by now, is a current that changes in its magnitude and direction. So if I were to sketch the voltage time graph of an alternating current power supply, you'll find that the voltage is increasing and decreasing, and the graph would be a sine wave. So not only is the voltage changing, the current is also changing, producing a graph in the same manner. By now, you should know that when current flows through a coil, it induces magnetism, causing the coil to be an electromagnet. If you're not too clear about that, please watch my video on electromagnets. Now, why is this important for the transformer? So we must understand that when current increases, the magnetic field strength increases. And when current decreases, the magnetic field strength decreases. When the current changes direction, the magnetic fields also will change direction. So to help you visualize this, I'm going to sketch on this diagram the magnetic fields. So let's say that when current is flowing through the primary coil in one direction, these are the magnetic fields that have been induced. As the current increases in magnitude, the magnetic field strength gets stronger, so you'll find that there are more lines representing the strength of the magnetic field. And as the magnetic field strength increases more and more, you'll find that the magnetic fields will cut themselves across the secondary coil. And then when the magnitude of the current decreases, then the magnetic field strength will also decrease. So the magnetic field strength would increase and decrease, and then when the current changes direction, the magnetic fields would also change direction. So it would then flip in the opposite direction, where now the magnetic fields are flowing opposite direction. So it's going to go this way now. So first the magnetic fields will be this way, shrinks, and then the other way, and then shrinks, and then so on and so forth. The process of the magnetic fields growing and shrinking will cause the magnetic fields to cut themselves across the secondary coil. This would cause electromagnetic induction, which is the process of inducing current in this other coil. And that's how current, and therefore electromotive force, is induced in the output circuit. So if you are not too clear about the process of electromagnetic induction or inducing current in a wire, then please watch my video on electromagnetic induction. So basically you can see the transformer is a combination of the process of induced magnetism and electromagnetic induction. So the reason why we need to use alternating current is because of the changing current value, which causes a changing magnetic field. And this changing magnetic field would cause the current to be induced in the output circuit. Because the source is alternating current, this process would also cause the induced current flowing through the output circuit to be alternating current as well. So obviously, if there are more loops on the coil, this would create a greater potential difference because there's more work done. So the more loops you have on the coil, the greater the voltage. The less loops you have on the coil, the lower the voltage. So this is how we can also change the voltage of the alternating current power supply. The purpose of the soft iron core is to help strengthen the magnetic field because, as you should have learnt by now, iron is a very good temporary magnet. Without the iron core, the magnetic fields can exist but would not be so strong, and the process of electromagnetic induction would not happen so easily. So the reason why we have the soft iron core here is to help concentrate the magnetic field so that the process of electromagnetic induction would be far more efficient than if you didn't have the iron core. So the purpose of the soft iron core is to help make the process of electromagnetic induction to be far more efficient. So, in summary, this is how we can describe the operating principle of a simple transformer. If you were asked to describe or explain the operating principle, think about the logical process. That means you start from the beginning and step by step explain what happens next. So the first thing you need to talk about is, of course, what's happening in the primary coil. Alternating current flows in the primary coil, which produces a changing magnetic field. The purpose of the iron core is to help concentrate or transfer the magnetic field from the primary coil over to the secondary coil. The changing magnetic field would cut across the secondary coil, which then in turn induces electromotive force in the secondary coil. So start with the primary coil, talk about how the magnetic field formed from the primary coil cuts across the secondary coil, which induces the EMF or current. Then the purpose of the soft iron core is to help concentrate or transfer the magnetic field so that the process of electromagnetic induction will happen more efficiently in the secondary coil. So just to give you an idea of what a transformer looks like in real life, so if you've seen this, there's actually a transformer inside. So even here you can see there are transformers because here are the wire coils and inside there's the soft iron core. So if you're wondering why there are so many wires coming out here, it's sometimes because they build multi-loop transformers where one transformer can produce many different voltages instead of just one output voltage. So now that we understand how the operating principles work, it should be quite clear to you that for a step-up transformer, there are more loops on the secondary coil, whereas for the step-down transformer, there are less loops on the secondary coil. This is the general symbol for the transformer. And as you can see, this is based on the construction of the simple transformer. You've got the iron core in the middle here, and then the primary and secondary coil. Now this symbol is used in general. It can be used for step up or step down, but sometimes in circuit diagrams, they may want to make it clear whether it's step up or step down. So whether it's a step up or step down depends on the ratio of the number of loops. So you can see here in the step up transformer, there are more loops on the secondary coil, whereas for the step down, there are less loops on the secondary coil. By the way, just to let you know, in these kind of symbols, the number of loops are not representative of the actual number of loops. It does not even represent the actual ratio of the transformer. This is just to show more loops or less loop, step up and step down. The actual number of loops or the ratio of number of loops does not depend on the symbol. It depends on what you're given in real life or in the question. Now, in addition to this, you also need to know the formula that relates the voltage to the number of loops. This applies to step up as well as step down transformers. It's quite simple. If the number of loops on the primary coil is NP and the voltage of the primary circuit is VP, whereas NS is the number of loops on the secondary coil and VS is the secondary voltage, the ratio is quite simply the number of turns on the primary to the number of turns on the secondary is equal to the primary voltage over the secondary voltage. So P represents the primary coil while S represents the secondary coil. N represents the number of loops or number of turns on the coil, whereas V represents the voltage on the circuit. So this is the formula that you need to know. This formula is actually really easy to remember because it's very straightforward. It's just a ratio of number of turns that's equal to the ratio of the voltage. And now let's look at the factors which affect the efficiency of a transformer. Now this is only covered in SPM. So if you're taking IGCSE, you can skip this part of the video and move on to the next section. Now, in addition to knowing the factors, you also need to know how to overcome these factors. You only need to know 4 factors and their solutions. The first factor is basically the heat loss in the wire coil. because anytime current flows through a conductor with resistance, heat will be produced for sure. If there's heat produced, that means there's energy lost in the form of heat, which would affect the efficiency because it takes away from some of the electrical energy that's being passed from the primary to the secondary coil. So how do we overcome this? We use thick copper wires with low resistance so that there will be less heat loss in the wire of the primary and secondary coils. Another factor you need to know is the heat loss due to the magnetization and demagnetization of the iron core. This is also known as the hysteresis loss. Now, what this means is that we know that the iron core will help to strengthen the magnetic field to enable the process to be more efficient. But if you use a magnetic material which does not magnetize and demagnetize easily, there'll be a lot of heat loss during this process of magnetizing and demagnetizing. So obviously the solution is to use soft iron. Some students may question, this is a strange factor, aren't we already using iron? So just to let you know, if you wanted to build a transformer using other magnetic materials like using steel, is it possible? Yes. But a problem with using materials like steel is that even though steel can magnetize and demagnetize, it does not happen easily and produces so much heat because it's constantly trying to magnetize and demagnetize, but it takes a long time and a lot of energy to make that happen. So that's why we don't use magnetic materials like steel. We use iron because it's easier, therefore less heat loss. Another factor you need to know is the heat loss due to eddy currents in the iron core. Now, what are eddy currents? This is actually a whole topic on its own, so I'll just simplify as much as I can over here. If you'd like to know more about eddy currents, I will be creating a separate video that will briefly explain about eddy currents. For now, let me just explain briefly so that you can understand what's happening in the transformer. When we talk about electromagnetic induction, we know that it's because magnetic fields are cutting across the coil to induce electric current. So this only happens when you have conductors for the secondary coil. But remember that for iron is also a conductor. So not only is iron helping to transfer or concentrate the magnetic field, what happens is the magnetic fields can also induce current in the soft iron core. The problem is that the current that flows through the iron core cannot be harnessed. We can't link it up to a circuit and make use of the current that's flowing through the iron core. So eddy current is basically current that has been induced and is flowing randomly on the iron material. And because iron has such high resistance, this can also produce a lot of heat. So in this case, you can think of the eddy current is rather useless in this situation. So how do we overcome this? We use a laminated iron core. That's because if you use one big piece of iron, because the area is so big, the current can flow easily, so there'll be a lot of eddy current producing a lot of heat. What are laminated iron cores? Basically, they're thin pieces like this which are laminated. The lamination here refers to insulation placed between each core. So an example of lamination here is that they will use insulated paint. So they get very thin pieces of iron, they put paint in between, and then when they stick them together, because there's insulated paint in between, it prevents the iron pieces from joining together to be one giant iron piece. So because each piece is now so thin, eddy current can still flow, but it's not induced easily because of the high resistance. So very little current is now flowing through each piece. So less eddy current, therefore less heat loss. This will not affect the magnetism because, as you should know by now, magnetic fields are not affected by shields. For example, if you place a piece of paper between a magnet and another magnet, the magnetic force would still work. So same thing in this case, even though there's lamination between each iron piece, collectively, the induced magnetism of the iron would still be functional. So when you put all these pieces together, magnetically, they behave as one big piece of iron core. But in terms of current flow, it will not flow easily because of the lamination in between each piece. And the fourth factor you need to know is the leakage of the magnetic flux. Now, what we mean by leakage over here, well, if you understand the operating principle, it should be quite obvious to you that there's quite a wastage of magnetic fields because During the process of induced magnetism, there's only one set of magnetic fields from one side that will be cutting across the secondary coil. On the other side, it kind of goes to waste because they're not cutting across any secondary coil. So that's what we mean in this case by the leakage of magnetic flux. So one way to overcome this leakage is to wind the primary and secondary coil over the same section. For example, like this. So you overlap the primary and secondary coil. So as long as they're insulated and they are connected to their own respective circuits, there will be no transfer of current. What you'll find is that the magnetic fields that are produced by the primary coil would immediately overlap the secondary coil, causing no leakage of the magnetic flux and producing a far more efficient electromagnetic induction process. So these are the factors which affect the efficiency of a transformer and how to overcome them. Now, let's look at how to calculate the efficiency of a transformer. Now, to calculate the efficiency of a transformer, we will use the efficiency formula, which you should have learned by now. There are two formulas to calculate efficiency. One is based on energy and another is based on power. To calculate the efficiency of a transformer, we will be using the efficiency formula based on power. So the formula involving power for efficiency is this. Efficiency is the output power divided by the input power times 100%. Now, because a transformer is an electrical device, we're going to calculate electrical power. Electrical power is calculated as the product of current and potential difference. So the output power is the power on the output circuit. So just to help you visualize, this is the input circuit with the alternating current power supply, and this is the output circuit with the load. Remember I mentioned earlier that the current and potential difference of the circuits are exclusive from each other. They have their own values of current and potential difference. So on the primary coil, the current flowing through the primary coil would be the primary current, which I'll label as IP, and the potential difference is VP, primary voltage. Whereas on the secondary coil, it has its own current, which I'll label as IS, secondary current, and it has its own potential difference, which I'll label as VS, secondary voltage. So from this formula of P equals IV, we know that the power on the input circuit would be IPVP, whereas on the output circuit, it would be P equals ISVS. What we know now about the electrical power of each circuit, we can substitute this into the efficiency formula. So from here, we have efficiency equals to, the output power is on the output circuit. So therefore, we can put ISVS on the top. Input power is the power on the input circuit. So that would be IPVP. And we multiply this with 100%. Now, if you come across a question that tells you that the transformer is ideal, what is ideal? Ideal means, oh, the perfect situation, right? So an ideal transformer ideally should have no loss in efficiency. That means an ideal transformer is 100% efficient. So if the transformer is ideal, that means there's no loss of power. Therefore, the input power would be equal to the output power. That means IPVP equals to ISVS. So for those of you who are studying IGCSE, you actually only need to know this formula. The questions they ask you tend to focus only on ideal transformers. IPVP equals ISVS. For those of you who are taking SPM, you may be required to use the efficiency formula if you have a transformer that is less than 100% efficient. But if you come across a question which says ideal transformer, then you use this IPVP equals ISVS formula. So I'm just going to write this for your information, that this is for SPM only, whereas for IPVP equals ISVS, this is for both SPM as well as IGCSE. So just to point out to you something I mentioned earlier about the changes in voltage and current. So I'm going to use the 100% efficient formula in this case to make this easier for you to see. If the input power is equal to the output power, that means VPIP equals to VSIS. So if you have a step-up transformer, what happens is the secondary voltage would be increasing. So I'm just going to draw symbols here to help you visualize. If the secondary voltage has increased and the input power remains the same, in order to balance this out, the secondary current has to decrease. So an increase in Vs will cause a decrease in Is if VPIP, which is the input power, remains the same. Whereas for a step-down transformer, again, if the input power, VPIP, remains the same, a decrease in Vs would require an increase in Is to remain the same. So a decrease in VSIS causes an increase in Is. So this is a mathematical thing. If you want to just give this a try, you can put in some numbers to figure it out. So let's just put some numbers here so that you can see it mathematically proven. So for example, let's say VP was 12 volts and IP was 2 ampere. So if we have a situation where the secondary voltage is increased to 24 volts, the calculation here would be like this: 12 times 2 equals to 24 times Is. So when you work this out, you would get Is as 1 ampere. So you can see that from 2 ampere, the current has decreased to become 1 ampere. So an increase in Vs has caused a decrease in Is. So an increase in the secondary voltage has caused a decrease in the secondary current. Whereas if we were to decrease the secondary voltage, let's say we drop this down to 6 volts. So this would give us 12 times 2 equals to 6 times Is. And when you calculate it, you're going to get Is as 4 ampere. So you can see how a decrease in the secondary voltage has caused an increase in the secondary current. So that's why I mentioned earlier that when you want to remember step up and step down transformers, you need to remember and explain in terms of voltage. Step up transformers would have an increase in the voltage but a decrease in the current, whereas a step down transformer has a decrease in the voltage but an increase in the current. So that's why we don't talk about current, we only talk about voltage when it comes to transformers. So what are transformers used for? They're actually used for the transmission of electricity, especially over long distances. So this is what happens during the transmission of electricity. So we have the power station. This is just a picture to represent any power station. Although here's a nuclear power plant, of course different countries do have different power stations. So for example in Malaysia, we have coal stations as well as hydroelectric dams. So this is just a representation of all power stations. So the power station is generating power. We will use a step-up transformer to increase the voltage from, let's say for example, 25 to 400 kilovolts. So we transmit electricity at extremely high voltages, especially over long distances. And then when it comes to the consumers, we will need to decrease the voltage so that they can be used. So first we step down so that heavy industries can use them, because heavy industries have very high demands for electricity. So we'll use a step-down transformer first to decrease the voltage from about 400 to 33 kilovolts. Then this is further decreased by using another step-down transformer for light industries, which also have a high demand of electricity but at a lower rate than the heavy industries. So this could be reduced from 33 to 11 kilovolts. And then this is further reduced down to 240 volts with another step-down transformer for the use of homes, offices, and schools. In addition to knowing about the transmission of electricity in terms of the voltages, you also need to know that electrical transmission happens in a grid. So it's not a single line from the power station all the way to the consumer. So the transmission of electricity happens through a grid with many interconnecting lines. And the reason why we have a grid instead of a single connection from power station to consumer is because in case any of one of the lines need to be taken down, there will still be alternative routes for the current to be transmitted. This is because sometimes there could be a power failure or a station that goes down for whatever reason, or sometimes we may need to close down one of the substations or transmission channels for maintenance. So you can't have a situation where you cut off the line and okay, sorry everyone, you get a blackout for the next 3 days, right? So that's why we have a transmission grid, so that in case we do need to take down one of the substations, there will be alternative routes for currents to still be supplied to the consumers. So now a common question when it comes to electrical transmission is, why are we transmitting electricity at such high voltages? Why do we see the warning high voltage signs on all the electrical transmission towers as well as the substations? It's everything to do with the power loss. Now, the formula for power loss is P equals I squared R, where P is power, I is current, and R is the resistance of the cables. So the reason why we transmit electricity at high voltage is because, for one, there will be lower power loss, and secondly, there is lesser current flowing through the cables, which is actually safer because lesser current means that there's less chances for electric shock. What causes electrocution and electric shock is the high current. So we want lesser current. The main reason for the high voltage transmission is always lower power loss. So if you're asked for the reason, that should be the number one reason that you write. If they ask you for a second reason, then this is the second reason that you would write. So now I'm going to prove to you how high voltage produces lower power loss. So I'm going to put in some numbers here so that you can understand this mathematically. Let's say this power station is producing power at 100 kilowatts. So I'm going to write here 100 kilowatts. So the value of the power produced obviously is determined by the power station, because how much energy that they're producing per second, that's the power. So based on this power, the value of the current that will flow through the cable depends on how much voltage it has been set to. So for this, I'm going to show you the comparison of two numbers, one at a low voltage and one at a high voltage. So let's say we set a voltage at quite a low value. Let's say, for example, at 100 volts. Now, in order to calculate the power loss, we cannot use a value of V. We need to find out how much current flows through the cables. This is so that we can get a value of the current to put into the power loss formula. So how do we get the value of the current? First of all, you need to use the P equals IV formula to find out how much the current is. So power is the power produced by the power station, which is 100 kilowatts. So I'm going to put here 100 times 10 power of 3, unknown current, and the voltage is 100. So if you want to understand why we're doing this, it's because this is the power produced by the power station. It's set at this voltage. We need to find out how much current is flowing through. So from here, you'll find that the current is 1000 ampere. Next, we need to calculate the power loss. So let's say the total resistance of the entire cables used in this part of the transmission is 100 ohms. So to calculate the power loss, we will need to take P equals I squared R, where I is 1000 squared times a resistance of 100. So you'll find that there are a lot of zeros in this number here. You'll get 1 times 10 power of 8 watts. And you can see that this power loss is even greater than how much power is being produced by the power station in the first place. So which means that there is nothing left when it gets to the consumers. Now let's take a look at the numbers when it comes to high voltage. So let's say we set the voltage at 100 kilovolts, very high number. So the process of determining the power loss is again the same thing. First of all, you need to calculate the current that's flowing through the cables. So we'll use P equals IV. So we've got 100 kilowatts, so that's 100 times 10 power of 3, unknown current, and V is 100 kilovolts, 100 times 10 power of 3. So calculating this, you should get current of 1 ampere. Then the power loss is calculated using P equals I squared R. So I is 1, so that's 1 squared, times R, which is 100 ohm. So when you solve this, you're going to get 100 watts. And that means there's still quite a lot of power left when it gets to the consumers. So you can see from the comparison of numbers here, a higher voltage will cause lesser current to flow through the cables. The lesser current is not only safer, but in turn produces less power loss as the current flows through the cables with the same value of resistance. So that's why we transmit electricity at high voltages, and that's why we use transformers in the electricity transmission, so that we can easily change the voltage to be a high number, and then we decrease the number when it gets to the consumers. And that's it for this video lesson. So I hope you found this video to be educational and helpful. Do click like and subscribe for more free physics lessons. Do also check out my YouTube channel for videos on other topics you might find helpful. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. If you'd like access to notes, quizzes, and syllabus updates, do check out my website at physicsrocks.com. Happy studying!